In the last video for this week, we're going to see if we can do better than the computer. Now, I wrote computer here thinking that you're using our TI Inspire software on your computer, but if you have the handheld, then we'll see if we can do better than your calculator. This is Unit 3, Part 2, Lesson 4. So here's a set of data. Normally I'd have this on the board in the classroom, and I'd like for you to use your graphing calculator to find the exponential regression for the data. Now, this type of problem was completed during the last unit as well, only we were using linear functions back then. Now I want to use the exponential regression. So if you recall, when we turn on our calculator and go to the home page, we're going to select a new document, and if we're prompted to save the last user's work, we're going to say no to that. And this time we want to add a list and spreadsheets page. The data that we're provided gives us what we call an independent variable and a dependent variable. Traditionally, the independent or X variable is on the top row, and the dependent or Y variable is on the bottom row if we've got two or more rows of data. When oriented vertically, as in the calculator, we would label that independent axis on the column on the left. So I'm just going to type in time here, and then we'll put our dependent variable on the right, and I'll type in temp. If you're using your computer with a keyboard attached, mine's a touch screen and doesn't have a keyboard attached, but if yours does have a keyboard, then you can actually type using the keypad on your computer rather than using your calculator, the emulated calculator on the screen. From here, we've got a bit of a tedious task. We've got to copy all of the information from the given chart into our calculator. Fortunately, in this case, the time values are they're all uniform, so we can enter those fairly quickly running down the page. But our temperature data, well, that's not so uniform, and we've got to reference this handout or this screen pretty regularly as we enter the data. For me, that means flipping back and forth between screens, and I'm not going to show that whole process. I'm just going to pause the video and complete this on my own, and I recommend that you do the same. Resume playback at a moment to check your work. And okay, I've got that data entered onto my calculator. Now remember, we can't leave our cursor active in this last position here. We have to press enter or click away from that last data point in order for the number to be stored in the calculator. So please make sure that you do that when you're trying this on your own. Additionally, I wanted to point out that there's another view for our calculator if it might help when you're working on the computer. If you look in the top right-hand window of the TI Inspire software, there's a key that says Document Preview. Right now, this software is emulating what the calculator would look like, and it even recreates the calculator screen and its precision. If we click this button and switch to computer instead of handheld, we're going to see the document as the computer would present this. And now we get a little bit more clarity and smaller font, if you will, that allows us to see more of the data at once. It's also going to make our graph a little bit more visible as well. So for the remainder of this video, I'm going to complete this in the computer preview as opposed to the handheld preview. I'm going to adjust my window sizing just a little bit so that hopefully it's still legible on your screen. Now once we have the data entered into a list and spreadsheets page, we have to organize a data and statistics page. And normally we would just press this menu key and then bring up the menu. I'm sorry, not the menu key, but the doc page and create a new document sheet. But I did want to point out here that when you press the menu key on this keyboard, the menu doesn't pop up on the screen. Instead, in order to get the menu to display while you're in the computer preview, you have to press this key here. That's what would bring up our menu option. So I'm going to be referencing that in a few moments as well. So anyway, I'm going to press Control Document. This will create a new page. And when we click on the screen, we can specify which type of page we would like to see. In this case, we've used the list and spreadsheets to store our data. Now we're going to add a data and statistics page to organize it. All of the data points are scattered on the screen here. So if we Scroll to the bottom and click the variable. Let's place our time variable across the x-axis. Then we can move over to the left and select the temperature variable along our y-axis. And here we have the data points as they decrease over time, and you can see that the shape here is generally exponential, or I suppose logarithmic if you adjust your point of view. And again, the computer can predict our best fit, our line of best fit, if we ask it to. So we're going to press the menu key, but again, the menu doesn't do anything for us. So I'm going to press the menu key here. And I'm going to choose option number 4 to analyze this graph, and then I'll choose option 6 again to find our regression options. The regression that I'd like to see this time is not the logarithmic, although one might work for us. I would like to see the exponential equation that the calculator thinks is the best fit. And there we have it. According to the calculator, the best fit for this particular set of data is this equation right here. Now that's the result that the calculator predicted, and it says it's got a pretty good fit. The r-squared value is 0.9812, where a score of 1 would be a perfect fit for the data. Now this result was determined to be the best fit of an exponential function in this format, ca to the x power. So according to the calculator interpreted our initial value to be 66.451, and it determined that our growth factor was 0.9997. Now keep in mind that even though we call this a growth factor, when this number is less than 1, if a is less than 1 but still positive, it has to be greater than 0 always, but if it's less than 1, then this implies that we have a decay. And we can actually subtract the difference. In this case, the difference between 1 and 0.9997 is 0.0003, which would be a 0.03% decay. In other words, the temperature is dropping 0.03% per second, since our time was measured in seconds. That may not have been clear, but it was. It was measured in seconds time, and our temperature is degrees Celsius. And I suppose that formula would work. I mean, if I wanted to know what the temperature of the coffee would be at 809 seconds or 912 seconds, I could certainly use this formula and substitute whatever time that I would like in for value x. And that'll produce a result that's on the black line, and that would be pretty close to where the blue dots exist. However, if we extend our time beyond 1800 seconds, or 30 minutes, you'll notice that the black line seems to be diverging or moving away from the trend of these blue dots. And all the way back here at the beginning, the actual temperature is a little bit warmer than what the trend line predicts. And so what I want to know is if we can do better than what the calculator has done for us. And I would say yes, we can, especially since we are aware of the notion of this ambient temperature. If the temperature of the room is not 0 degrees, then we have to introduce this B value here. This is the ambient temperature at which the coffee, in this case, this hot coffee that's cooling, what the temperature of that coffee is going to approach. If the room is 20 degrees outside, or 20 degrees in the room, I should say, the coffee would never cool down to 0 degrees. That would be colder than the room is itself. But back here in this exponential format, that's exactly what's implied by this function. There is no b value indicated, therefore this function will tend or level off towards 0. So in the classroom that I'm recording this video in, the ambient temperature is 20 degrees Celsius. So I'm going to change B to 20. I'm going to keep in mind here that while we had all of these data points, wherever they were, what I want to keep in mind is that these data points are not leveling off at 0 on the on the x-axis. They're leveling off here at y equals 20, at y equals 20 degrees. And that 20-degree mark where the trend line is leveling off is represented by that b value. And I should be a little bit more careful, even though this is a generic sketch, that at time 0 we had a high temperature, so that first data point is right on the y-axis, so maybe I'll put my dots like this. And how that might be helpful for me is in this consideration. The c value, which we know is our initial value, is the difference or the distance between this horizontal asymptote and our first data point on the y-axis. Historically, that number is simply the y value of this data point, but let's keep in mind that since we have this offset, this b value offset, the c value distance is really measured from, in this case, 20 to the value of our highest point. And so if I switch over to the calculator and I hover my cursor over this first data point, that's along our y-axis when x is equal to 0, we have a data point of 0, 70.3. So at time 0, we've got a temperature of 70.3. At time 0, we've got a temperature of 70.3. So that tells me that the difference between 70.3 and 20 is our c value. So I'm going to say that c is equal to 50.3, and I'm going to continue to build this better function. So we now have a 50.3 times a to the x power plus 20. And we almost have a function that works. We would like to build this function based on the variable x, but currently we don't know the growth factor. We don't know the rate of decay in this particular case, and that's our a value. The nice thing is that all I need to do is choose one data point from this list of 15 or so. Actually, there are 16 if we count this initial point. So we have 16 data points. All we need to do is pick one of those data points, and we can establish our a value. And here's where the problem becomes a bit subjective, because if I choose my data point here, my second data point here, then I'm going to create a different growth factor than my neighbor who may be choosing this data point there. If I choose this data point, then my growth factor is going to be different, and so on. And while it's not critical which one we do choose, it is important to note that our answers may differ from one another if we pick different ones. Now, since I enjoy doing math so much, I tend to perform this next step 2 or 3 different times, and I'll usually pick a data point somewhere in the middle and calculate my a value. Then I'll pick a data point at the end, calculate my value, and if I think I can do better than either of those 2 attempts, then I'll make a third guess on my a value in between. But for the purposes of this video, I'll just choose one data point. Let's just choose the one at the end, and we'll see if we can make a better fit, because we noticed that our first data point and our last data point were farthest from the original equation. So let's see if we can get those included in our graph. So I'm going to make a note that this data point here was at an x value of 1800 and a y value of 42.4. So we've got one other data point. We're starting here at the beginning and we're ending here at the end. And this last data point was 1800, 42.4. That's going to be helpful because we now know that the function, when evaluated at 1800, would be equal to 50.3 times a to the 1800th power, because we changed the letter x to 1800, plus 20. And we also know that the function result at that data point was 42.4. The y value when x was 1800, that's what our function notation is telling us, our y value was 42.4. And now we've got 50.3 times a to the 1800th power plus 20. Now this turns into an algebra problem. What would it take to solve for a? How could we get a by itself? Go ahead and pause the video now and try this portion of the problem on your own. I would prefer to see an exact answer for a where no calculator is used. Resume playback in a moment to check your work. And while there are some intermediate steps that we should show, the point here is that in order to isolate A, I had to first subtract 20 from 42.4, then divide that result by 50.3, and then ultimately take the 1800th root of that expression, and we are left with our result for A. And this is perfectly acceptable. This expression for A is perfectly fine because it does tell us exactly what A is equal to, and we didn't have to use a calculator yet. We haven't lost any accuracy due to rounding after reading the result from the calculator. Now, one last time, why this is so helpful for us is because now we have obtained our A value. We interpreted the original graph and our knowledge of the situation to obtain our B value. And we interpreted our graph for the C value. So we were able to identify with just 2 data points our A, B, and C value, and ultimately we've now established a function based on X that should predict the temperature of this hot coffee in a slightly better fashion than what the calculator has done for us. So we've got 50.3 times the 1800th root of 42.4 minus 20 divided by 50.3 raised to the power of X plus 20. Now, let's see how that graph compares to the original graph that the calculator presented. If I switch to the calculator screen and choose the menu options, I can choose to analyze option 4 and then plot our own function number 4 as well. And this function can be anything that you'd like. In this case, we're going to use the equation that we just established. 50.3 times the 1800th root, whoops, let's try that again, 1800th root of the fraction, so I press Control divide, 42.4 minus 20 over 50.3. All of that's raised to the power of X. And notice I'm using the right arrow key to move outside of the grouping symbols, and in this case to move outside of the exponent as well. And now we can add 20, and we're adding 20 to the exponential function, not adding 20 to the exponent itself. And so here's the moment of truth. How'd we do? I think we did okay. I don't know that this is much better, and I'm going to change the color here just to make it stand out. So the line color is going to be switched to blue now. We got a little bit farther away from the middle than the original example. This blue line is a little bit too far from the middle, but you know what? It struck this first point and this last point precisely, so that's pretty good. If I wanted to manually adjust this, I would try to make this blue line's graph a bit steeper, quote steeper. I want to see if I can make it a little bit steeper so that it gets to be closer to the data points, and that'll give me a better predictor for future values. And I would do that by calculating the A value here to a decimal point, maybe 4 or 5 decimal places, and then we can adjust it from there as we've seen in prior videos. But I'm going to leave this one as it is in the interest of time, and I'm curious, did any of you use a different data point and obtain a better fit for the graph? If you did, make sure you tell me in your notes so that I can see what you've done. To finish the video, I'd like to talk about what we call a logistic function. Logistic functions are nice because they give us a way to put a cap or an endpoint on our exponential functions. For example, if we had an exponential function that describes the growth of a population, technically speaking, an exponential function, once it starts racing upward, it races upward towards infinity and it never slows down. That would be impossible for a lot of real-world applications, specifically a population. There's no way that a population can reach infinity. There are limiting factors that prevent that from happening. Physical space, access to food and water, disease, etc. There's often what we call a carrying capacity or a limit to that population. And while that population growth might be increasing on an exponential curve at the beginning of this cycle, a lot of times there's a point of inflection where that curve changes from an increasing exponential function to an increasing logarithmic function. And it sort of turns and it levels off and it reaches some sort of what we call carrying capacity, some upper limit, some upper behavior. And this is what the general graph of a logistic function will look like. And those are generally accomplished by creating fractions with exponentials. And there are other ways to create them too, but in this particular example, that's exactly what we have. We've got a fraction that's created with an exponential function sitting in the denominator of that fraction. This particular mathematical model or function has been developed from prior space shuttle launches, and it tells us the relationship between the Fahrenheit temperature, the temperature outside in Fahrenheit, around the O-rings that I believe are in a fuel system for the space shuttle. Now, evidently, these O-rings become eroded or start to leak based on different temperatures. They're susceptible to the temperature. And this particular model indicates that there are 6 O-rings. The number 6 here indicates that there are 6 O-rings on this shuttle. And we would like to know how many O-rings are likely to be eroded or leaky when the temperature is 80 degrees Fahrenheit. Now, personally, I feel that this type of question lends itself to function notation a little bit better, so I'm going to switch that here. I'm going to say f of 80 because the result of the function based on the 80-degree temperature is equal to 6 divided by 1 plus e to the negative parenthesis 5.085 minus 0.1156 times 80. And there really isn't any algebra that has to be done here. We were given the most important piece of information that we needed, the temperature, x, and now we can just reach for the calculator and compute what the end result is. So I'll switch to the calculator. I'll press Control, Doc, and I'll add a new page. This time I'll add a calculator page to my document. And I'll switch back to calculator preview just so that the text is a little bit larger on your screen. And I'll enter the expression. We've got a big fraction with a numerator of 6 in the top and 1 plus e to the negative power grouped by parentheses 5.085 minus 0.1156 times x. X in this case happens to be 80, so we'll close the parentheses around that. You could have used a multiplication sign as well, and I'll close the parentheses here. And I'll pause for a second. I'm going to ask myself, does what I have in the calculator match what I had on paper? 6 over 1 plus e to this power. We had a negative exponent, 5.805 minus 1156 times x. That looks pretty good to me. So I know I want the decimal result here. I don't want the exact answer, so I'll press Control and then Enter. And the result is 0.0919. 0.0919. But what's our unit? What's that mean? Well, remember, the result of this function is the same as our y values. And our y values back here were telling us the number of eroded or leaky O-rings. Now, I don't think it's possible to have 0.09 leaky O-rings, so I would interpret this as, I'll just use my units here, O-rings. I would interpret this as saying that there are no leaky O-rings at 80 degrees Fahrenheit. And I assume that's a good thing. We don't want any leaking or eroded O-rings at ambient temperature. When the space shuttle is just sitting on the launch pad, we don't want to have any of that fuel leaking. Okay, so we know that there aren't any leaking at 80 degrees, But maybe there's heat from the engine that's going to surround this, and maybe the temperature can get much higher than 80 or 90 or even 100 degrees. And maybe we're worried when the temperature is high enough to produce 3 leaky or eroded O-rings. Maybe that's the failure point. We won't launch this shuttle if we think 3 or more are going to be eroded. So what is the X value? What is the temperature that's going to make that happen? Well, we can set up an equation to solve for that as well. So our target is 3. We don't know the X value that's going to make that happen, but our target is 3. When does 3 equal this function? E to the negative 5.085 minus 0.1156x. And now all we've got to do is go after this x value. Do you have any ideas on how we can isolate that x? This is going to be a challenge of your algebra skills to see if you can make it happen. If you're stuck, let me give you a hint. The number 3 could also be written as the number 3 over 1. And if we have two fractions that are equivalent to each other, there's a very common technique that's used to solve that. Can you think of it? Go ahead and pause the video now and try solving for x. I'll come back in a moment to show you how I would approach this problem. Well, usually when I see that two fractions are equivalent, or if I can set up an equation that make two fractions equivalent, I'll immediately think of the cross products across the equal sign. Because I know that when two fractions are equal, then their cross products are also equal. That means that whatever 6 times 1 is, must be equal to whatever 3 times this denominator is. And by multiplying across the diagonal like this, we can eliminate the fraction. And I know that a lot of us are not real comfortable working with fractions, and with it now gone, we might be off to a pretty good start in solving for x. So I'm not going to distribute this 3 into this group. You could if you wanted to, but I think that makes more work for you than necessary. Because again, our job is to get x by itself. We're peeling away the components that surround this x, since it's buried so deeply inside of grouping symbols. And I think the next thing that I'm going to do is divide both sides by 3. That leaves me with 2 equals 1 plus e to the negative power here. And while I'm copying these numbers from above, I'm thinking about my next step. I think my next step is to subtract 1 from both sides. And now I have an expression, or I should say an equation, of an exponential whose base is e. The exponent contains our variable, so in my mind I'm thinking logarithm. A logarithm would be very helpful in order to isolate the value x, since it's in the exponent. And I know that when I rewrite this exponential as a logarithm, I would need the logarithm base e, evaluated at the number 1, and that's going to be equal to the result of the exponent. Now I'm getting kind of tired of using this negative sign with a set of parentheses, so I'm going to distribute it at this point. I'm going to write negative 5.085 plus 0.1156x. Now I don't need those parentheses anymore. And I'm also going to note that the logarithm with a base of e is really what we call a natural logarithm, and I'll write natural log of 1. And I'll also remind you that the natural log of 1, or any logarithm of 1, is equal to 0. Remember that from our log properties? Logarithm base a of 1 always equals 0, because it's a, some base to the power of 0 that will equal 1 if we consider our loop rule. So this natural log of 1 is just 0, and now we're just left with a linear equation that we need to solve. So I'll add 5.085 to both sides, and then divide by 0.1156, and that'll leave me with 5.085 divided by 0.1156, and that's our x value. And on our calculator, I did that off off camera there. 5.085 divided by 0.1156 is 43.9879 degrees. And this is degrees Fahrenheit. And so my comment earlier about the engine making the air temperature too hot might cause leaky O-rings, and maybe I was going in the wrong direction. Evidently, it looks like it's the cooler temperatures. It's the cooler temperatures that affect these O-rings, because what we've just found is that with an X value of 43 degrees, or 44 degrees if you rounded it to the nearest whole number, with an X value or an outdoor temperature of 44 degrees, then we will predict that 3 O-rings will have failed, either become eroded or leaky. So we wouldn't want to launch this shuttle. Now, they normally launch from Florida or Texas, so we definitely don't want to try launching this shuttle if the temperature outside is around 44 degrees. 80 degrees is good, 44 degrees is bad. So I know that's a lot to take in one video, so I want to make sure that you do have some chances to practice this. There are some logistic questions inside of our Math Excel problem sets. If you have questions or concerns on any of them, please send me a message and I'll try to address those concerns. Thanks for watching.